Hello students, how are you all? Welcome back to the second part of moving charges and magnetism. In previous, I did solve numericals up to 31, right? So let me start with 32 question. Okay, so let's get started. Okay, let me read it out. A long wire carrying a steady current is bent into a circular loop of one turn. Okay, so they said a long wire. What does it means? It's an infinite length wire. Okay, that wire is bent in the form of a circular loop. Let me show you that. You may get a doubt that is it possible for us to bend a infinite length wire in the form of a circle, isn't it? If you have any such kind of doubt, let's take a length wire, a length long wire, okay, and it is carrying some current. They didn't mention direction of current. You can assume as your wish, okay. So assume radius of this circular path is r. Then what's the formula for magnetic field at the center of a current carrying circular coil? B is equal to mu naught I by 2r, right? So 2r, mu naught I by 2r. This is the formula for magnetic field due to a current carrying circular coil at this center. Okay, so direction is into the board. Magnetic field direction is into the board. Okay, let's continue. Magnetic field at the center of the loop B, loop is B. Okay, it is then bent into a circular coil of n turns. The magnetic field at the center of this coil of n turns will be, okay. Now the same coil is coiled in n number of turns. When the same coil is converted into n number of circular coil, what happens to the radius of the circle? Decreases or increases? It's gonna reduces by how many times? N number of times. Okay, so look at this. Now the same coil is reduced into n number of coils. Its radius is reduces by n. And how many number of turns? Such turns are there? N number of turns are there. Now tell me what's the formula for new magnetic field? So let's say this is B dash. New magnetic field is mu naught I by 2r dash. This is due to one turn. As there are n number of turn, you just multiply it with n. So what's r dash? R dash is r by n. Then mu naught I divided by 2 times of r by n into n. N goes to numerator. It is going to be n square times of mu naught I by 2r. This n mu naught I by 2r is magnetic field at the center of a current carrying circular coil. Let me replace it. Then new magnetic field is going to be n square times of original magnetic field. Which option? Option B is the correct answer. Understood? Let's solve question number 33. A wire carrying current I has the shape as shown in adjoining figure. Okay, so this is the diagram. Linear parts of the wire are very long and parallel to x-axis. Okay. While semicircular portion of the radius capital R is lying on YZ plane. The magnetic field at point O is, okay. So this one I would like to convert into another format so that it is going to be easy for you to understand. Let me draw the diagram. A semicircular portion of radius capital R is on YZ plane. That's what I did represented. But there are two semi-infinite wires which are parallel to the x-axis. That is, it looks like out of the board, right? Or out of the paper that you are using, or out of the mobile phone. That I am going to represent like this. Just observe here. So if current is into the board, I am going to represent with a cross. If current is out of the board, I am going to represent it with a dot. So this is how I can change that. Okay, so now it's very easy to understand. So here current I is into the board, here current I is outward. Okay, so now by using a right hand rule, you can find out what is the direction of magnetic field due to these two conductors. These are semi-infinite wires. This is semi-infinite wires, semi-infinite length wire. So this is also semi-infinite length wire. So first of all, try to find out direction of magnetic field due to all this. Let me name this is as 1, 2, 3. So due to first conductor, as current is into the board, you know how to use right hand thumb rule, right? Place thumb in the direction of current. Curled fingers indicates direction of magnetic field. If you arrange like this, so this is the direction of magnetic field that you are going to get. So you are going to get in clockwise direction. So at this point, so this is how you are going to get magnetic field. This is the direction. So at this point, they are asking at point O, right? This is where they are asking magnetic field, right? So at this point, the direction of magnetic field is downward. Downward in the sense it is opposite to z axis, right? It is along minus k cap. That's all. So this is magnetic field due to first conductor. Similarly, observe this third conductor. So thumb represent direction of current, curled fingers indicate direction of magnetic field. So in this case, magnetic field direction is going to be clockwise or anti-clockwise direction. It's going to be anti-clockwise direction. So at this point again, direction of magnetic field is going to be downward itself. It is in the same direction of magnetic field due to the first conductor, that is, let's say B3 minus k cap. Hope you are understanding. Okay, so let's find out magnetic field due to the second wire. If you observe, and same process. Now you just place curled fingers in the direction of current for the semicircular wire. Thumb indicates direction of magnetic field. If you can use like that, curled fingers direction of current, thumb direction of magnetic field. You can use vice versa. In the previous class I told you, no? So in this case, magnetic field is going to be into. This is due to second wire. Into in the sense x-axis out of the mobile phone, minus x-axis is into the mobile phone. That means it is going to be minus I cap. So let me write down total magnetic field at point O. So B net at O is equal to magnetic field to first conductor, second conductor and third conductor respectively. Magnetic field due to first conductor is, it is a semi-infinite wire. So formula is going to be minus mu naught I by 4 pi capital R direction k cap. So this minus k cap represents direction of magnetic field. Got it? Next, B2 is it is into the board, right? So it's going to be semicircle. So mu naught I by it's a semicircular wire, right? So you are going to get 4R, direction minus I cap. So let me write down here itself, minus I cap. Next, B3 magnetic field due to third wire, that is also semi-infinite wire. So already given representation here, minus B3 is mu naught I by 4 pi capital R direction k cap. Okay, so this current is capital I, right? Okay, let me substitute that. Let's simplify this. So it is minus common, mu naught I by 4R is also common. So here I am going to left, in this part I am going to left with 1 by pi, and this part 1 by pi, total it is going to be 2 by pi, plus here I am left with 1. So this is k cap and this is I cap. So which option matches here? Oh, I have to remove pi also. Okay. So if I remove that pi, so minus mu naught I by 4 pi R pi I cap plus 2 k cap. This is the final answer. I think option C is the correct answer. Understood? Yes, option C is the correct answer. Let's solve question number 34. So what's the thing they have given? Two similar coils of radius capillary are lying concentrically with their planes at right angles to each other. The currents flowing in them are I and 2I respectively. The resultant magnetic field induction at the center will be. Okay, let me draw the circuit. This is how it is. So two circles are mutually perpendicular with each other and they are placed concentrically. Concentrically in the sense their centers are at the same location. This is how it is. Okay, both of them are having same radius. But the thing is they are carrying a different current. So current direction they didn't mention. Doesn't matter because you are going to get magnetic field due to these coils in perpendicular direction. They're asking only magnitude, so that's why there is no any problem of assuming direction of current. So let me assume, so this is the first coil, current flowing through the first coil is I, and let's say current flowing through the second coil is like this, okay, and this is 2I. So what about magnetic field direction due to first coil? If that's the direction of, place curled fingers in the direction of current and you can get the direction of magnetic field by using thumb direction. Can use that. So can you tell me the direction? Can you guess the direction of magnetic field due to first conductor? Yes, it is towards left. This is B1. What about direction of magnetic field due to second conductor? It's going to be downward. Use right hand thumb rule. Curled fingers direction of magnetic field, curled fingers direction of current, thumb indicates direction of magnetic field. This is going to be B2. Okay, so as these two are at an angle 90 degrees, then how to find out B net? By using parallelogram law, right? So let's find out that. First of all, what is magnetic field due to first coil? B1 is equal to mu naught I by 2R. Magnetic field due to second conductor mu naught, it is 2I by 2R. As they are mutually perpendicular with each other, then B net is equal to square root of B1 square plus B2 square. If you observe one thing here, mu naught I by 2R is common, so just bring it out, mu naught I by 2R. So I'm left with root of I square, mu naught 1 square plus 2 square, so 1 square plus 2 square. So final answer is root 5 times of mu naught I by 2R is the answer. Which option matches? Mu naught root 5 times of mu naught I by 2R. Option A is the correct answer. Understood? Let's solve the next one. Charge Q is uniformly spread on a thin ring of radius capillary. Okay, let me draw it. 35. So this is how it is. Charge Q is spread uniformly on this. It is spread in the sense everywhere it is. Charge is at every position. So it is spread uniformly. Okay. Now this ring is rotating about its axis with uniform frequency. Okay, what is the meaning of rotating about its axis? Axis is passing through center of mass and perpendicular to the plane. This is the meaning. So rotating with a constant frequency f. Question they are asking, magnetic field induction at the center. What's the general formula for magnetic field induction at the center of a current carrying coil? That is mu naught I by 2R. Okay, so radius is R. Do I know current? No, I don't know. Is this coil is rotating or is this thin is rotating? Yes, it is rotating. If it is rotating, charge on the ring also rotate, right? So motion of a charge constitute a current. What's the general formula for current in terms of charge? I is equal to Q by T, right? So 1 by T can be replaced as Q into F, right? So Q and F is a given data in question itself. So convert the current in the form of Q and F, then magnetic field is going to be mu naught Q into F divided by 2R. So answer should be in terms of given data. Which option matches here? Option B is the correct answer. Understood? Okay, let's move on to the next question. A current loop consists of two identical semicircular pods, each of radius capital, one lying on xy plane and the other on xz plane. Okay, let me draw it. Just observe that diagram. So what's the radius of this is this capillary and it is carrying some current I, right? Okay, let me assume the direction. That's your wish because they're asking only magnitude, right? So if they are asking direction particularly, then they will give you the diagram. So they didn't give you any diagram and they're asking only magnitude. So direction of current is your choice. You can assume anything. Okay. Now, so first of all, find out the magnetic field due to first semicircular wire, first one and second one. As I said, use right hand thumb rule. So if you use, then it is going to be magnetic field is into the board for due to first semicircle. Now if you observe magnetic field due to this semicircle which is in xz plane, place four fingers in the direction of current. Thumb indicates direction of magnetic field which is downward. Okay, so this is B2. Let me write down equation. So B1 is equal to mu naught I divided by 4R. Direction is minus K cap. Similarly, B2 is mu naught I by 4R. Direction is minus J cap. Just check it out. Simply use right hand thumb rule, you'll get it. So as these two are perpendicular with each other, then B net is equal to root of B1 square plus B2 square. Mu naught I by 4R is common. I'm left with mu naught I by 4R root 1 square plus 1 square, which is equal to mu naught I by 4R root 2. Is there any option? No. So I have to convert this. Okay. So mu naught I by, so you can write down it is as 2 into 2, the 2 again root 2 into root 2 into R to root 2 will get cancelled out. So final answer mu naught I by 2 root 2 R. This is the way. This is B net. Magnitude of net magnetic field. Option A is the correct answer. Let's move on to the next one. 37. Two circular coils 1 and 2 are made from the same wire, but the radius of the first coil is twice that of the second coil. Okay, R1 is 2 times of R2. Both are made of same wire. Okay, what potential difference in volts should be applied across them so that the magnetic field at their centers is same? Okay, let me draw the circle. So one is of radius R1. So this is greater, right? Okay, this is of radius R1. Another one is of radius R2. So let's say as this is a closed path, it is of potential V1 and this is of potential V2. And current flowing through them is, let's say, I1 and this is I2. What's the formula for magnetic field? General formula for magnetic field due to a complete circle, it is mu naught I by 2R, right? It's magnetic field mu naught I by 2R. And we can replace I with potential, that is I is equal to V by R, right? So it's mu naught into V by R divided by 2 times of R. So finally mu naught V divided by 2R square. As they said, the magnetic field is the same. So as this magnetic field is the same, then potential is directly proportional to R square, right? So let me write a V1 by V2 is equal to R1 by R2 whole square, which is equal to R1 is 2 times of R2, right? So if you substitute it is as 2 times of R2, it's going to be 4. V1 by V2 is equal to 4. Actually, there is a slight difference in the question. Try to change that question as The resultant magnetic field due to two semicircular parts of the, sorry, not that one. What potential difference in this case? What is the ratio of potentials? That is the thing. So option C is correct for ratio of potentials. That's the correct answer. Let's move on to the next one. Question number 38. An electron moves in a circular orbit with a uniform speed v. It produces a magnetic field at the center of the circle. The radius of the circle is proportional to, okay, charge is moving in a circular path with a speed v and radius is smaller. Did they mention it? Radius? Oh, they didn't mention it. Okay, just assume it is as a smaller. What's the magnetic field at the center? It's mu naught I divided by 2r. It's not Kepler, it's smaller. So how to find out current? I is equal to q by t, right? So what is the time period, time taken by this charge to complete one circular path, which is equal to 2 pi r divided by speed. Okay, so let me substitute it here. What we are going to get? Mu naught qv divided by 4 pi r, right? It's going to be 4 pi r square. So this is magnetic field. Now they are asking the radius of the circle is proportional. So 4 pi is constant, mu naught and q is also constant, r square is proportional to v by b, and r is proportional to root of v by b. Which option? Option C is correct answer. Understood? Okay, so let's solve the next one. The magnetic field of given length of the wire for a single turn coil at its center is B. Then its value for 2 turns coil for the same wire. Okay, super. We did solve this question earlier. This question is similar to question number 32, exactly the same. So what's the relation for new magnetic field? 39 solution. So magnetic field new is equal to n square times of old magnetic field. What is the meaning of n here? Number of turns. How many number of turns they are asking? 2 turns. Then b dash is equal to, as if you square it, you are going to get 4 times of old magnetic field. Which option matches here? 39. Option C is the correct answer. Already we solved this. You just go through this. Question number 32 and 39 both are same. Only difference is they have given what is the small n here. That's all. Next, question number 40. Magnetic field due to 0.1 ampere current flowing through a circular coil of radius 0.1 meter and 1000 turns at the center of the coil is formula for magnetic field at the center of a current carrying coil. It's going to be 1000 turns into mu naught. Mu naught value is 4 pi into 10 power minus 7. Mu naught I value 0.1 divided by 2r. R value 0.1 meter. Formula is n times of mu naught I by 2r. This is the formula. I just substituted here. Mu naught 0.1 will get cancelled. So 1000 into 10 power minus 7 is 10 power minus 4. 2 will get cancelled. 2 pi is 6.28. 3.14 into 2, 6.28 into 10 power minus 4. Which option? Option A is the correct answer. Direct answer. Direct calculations. Let's solve next question. Magnetic field intensity at the center of the coil of 50 turns, radius 0.5 meter and carrying current of 2 amperes is same question. Just change in values. Magnetic field is equal to how many number of turns? 50 turns. Mu naught value 4 pi into 10 power minus 7. I value is 2 ampere divided by radius is 0.5 meter. So 2 into 50 is 100. 100 into 10 power minus 7 is 10 power minus 5. 2 into 0.5, this is you are going to get as a 1. So it's going to be 4 pi into 10 power minus 5. So final approximately answer we are going to get 1.25 into 10 power minus 4 Tesla. Option B is correct. Next, question number 42. A coil of 1 ton is made of a wire of certain length, and then from the same length a coil of 2 tons is made. If the same current is passed in both the cases, then the ratio of magnetic induction at their centers, again same numerical, 39, 42 and 32. All these are of similar model. Question number 42 answer. What's new magnetic field formula? So new magnetic field is n square times of old magnetic field. Also we can write down it is as B2 is equal to n square times of B1. They're asking ratio of B1 by B2. So you can write down it is as 1 by n square. What is n here? N is equal to 2, right? Then what's going to be the answer here? 1:4 is the correct answer. Which option? Option B is the correct answer. Understood? Super. Now next topic is Ampere's circuital law. Okay. It is somewhat similar to Gauss law in electrostatics. We are using Gauss law to find out electric field at different locations. Right. Similarly, Ampere's circuital law we are going to use to find out magnetic field, and it is an alternate method to find out magnetic field due to current carrying wires apart from Biot-Savart's law, right? Okay, so let me start with question number 43. So it's a graphical question. A cylindrical conductor of radius. They said a cylindrical conductor, it means it's a solid conductor. Radius is capital, is carrying a constant current. The plot of the magnitude of magnetic field B with a distance D from the center of the conductor. Super. Just check out the formulas that I wrote over there. So these are the formulas of magnetic field inside, outside, on the surface of a current carrying coil. This is how it is. So radius is capital R. If inside at a distance is small d, form of magnetic field is this one, and inside magnetic field is directly proportional to D, and this is on the surface which is constant. Outside it is inversely proportional to D. So if you observe the graph here, as it is directly proportional to inside, so you are going to get a straight line, then it reaches to maximum, then after it will reduces. This is the graph. Which option matches? Option D is the correct answer. Understood? Next, a long straight wire of radius A carries a steady current I. The current is uniformly distributed over its cross section. The ratio of magnetic fields B and B dash at the radial distances A by 2 and 2A respectively from the axis of the wire is. Okay, so 44. Let me draw it. So I'm just going to show you the top view of this conductor. It's the radius of it. Radius is A. They're asking magnetic field at A by 2 and another position is 2A. These are the two locations they're asking magnetic field. Okay, let's find out. And they said it is a long straight wire. Does it means a hollow wire or a solid wire? It's a solid wire. Okay, let me draw a Ampere's loop here. So this is how it is. I need magnetic field due to this and magnetic field outside. If you observe one thing, this is B2 and this is B1. So this complete conductor is inside of loop 2 or loop 1. It is completely inside of loop 2. First of all, let me find out magnetic field due to outside, due to this conductor outside, that is B2. So what is Ampere's loop, Ampere's circuital law formula? Integral B bar dot dl bar is equal to mu naught into I inside, right? So if we observe for loop 2, complete conductor is inside. So I inside is going to be I itself. So into B integral dl, which is equal to mu naught into I, where integral dl is total length, so it's going to be 2 pi r is 2a, which is equal to mu naught I. So final formula for magnetic field is mu naught I divided by 4 pi a. So this is magnetic field due to outer loop. Okay, let's find out magnetic field due to inner loop at a distance small. First of all, I have to find out current. So as current is flowing through the conductor throughout its area, so which is current density is going to be constant and current I is directly proportional to area. So for pi a square area, what's the total current flowing? I. Then for pi a by 2 square area, what's going to be current? I have to find out that inside current, that is I dash is equal to, we know the procedure. I've been using this trick now for proportional relation, just understand this. So it's going to be pi a square, pi will get cancelled into I. A square also will get cancelled. Now current flowing through the loop of radius a by 2 is I by 4. Then magnetic field B1 is equal to mu naught I divided by, so magnetic field at the center, it's going to be, you just apply what do you call, Ampere's law. That is the easiest one. So integral B dl is equal to mu naught I inside. So B1 integral dl is 2 pi r radius is a by 2, so which is equal to mu naught into I dash. So where I dash is equal to I by 4, right? Let me substitute it. So I by 4. 2 1s are 2 will get cancelled. So B dash or B1 is equal to mu naught I by 4 pi a. If you observe one thing here, B1 and B2 both are same. So B1 by B2 ratio is going to be 1. Option 1 is the correct answer for question number 44. Okay, understood? Next. Two identical long conducting wires AOB and COD are placed at right angles to each other with one above the other such that O is their common point for the two. Okay. They didn't give the diagram, so we just have to imagine. So this is how O is the common point for both of them. The two wires carries currents I1 and I2, currents I1 and I2. So they didn't mention in which direction. You can assume as your wish. Point P is lying at a distance D from O along the perpendicular direction to the plane containing the wires. Okay. Observe these diagrams. The question is a little different. What you have to do is just observe, place two pens like this, like a plus symbol, and from the center, perpendicular to those two pens, you have to find out magnetic field at a distance. So this is where they are asking magnetic field. Due to this conductor AOB, magnetic field at this point is going to be downward. Let's say this is B1 and due to conductor, see it is going to be into the board, so this is how it is going to be. Let's say this is B2. You can find out these directions with the help of right hand thumb rule. Okay, don't get confused, nothing is there to get confused over there. So as they said, they are of long straight wires. Okay, so let me write down formula directly. So as these two are perpendicular with each other, one is into the board, another one is downward. So B1 is equal to mu naught I1 divided by 2 pi D, and B2 is equal to mu naught I2 by 2 pi D. Okay, so what's the answer? So as these two are perpendicular, B net is equal to, these two are perpendicular with each other. So mu naught by 2 pi d is common. Mu naught by 2 pi d Root of I1 square plus I2 square is the correct answer. Option D is the suitable answer for this question. Understood? Next question number 46. Magnetic field at the center. Okay, these are a long straight wires. So if you observe here, magnetic field due to first one, it is B1, which is into the board. Use right hand thumb rule. Due to second one is B2, which is out of the board. And they are asking exactly at the center, right? As current in first conductor is greater, definitely B1 is greater. So let me write B1 is equal to mu naught I. I is okay, leave it. Mu naught I1 divided by 2 pi d. Similarly, B2 is equal to mu naught I2 divided by 2 pi d, as distance of separation is same. So as denominator is same for both cases and I1 is greater than I2, so I can subtract them. B net is equal to, and one more thing, there in opposite direction. B1 is into, B2 is outward. So it's going to be B1 minus B2. So mu naught by 2 pi d is common. I1 minus I2 will be there. Let's substitute the values. So in this case, B net is equal to mu naught is 4 pi into 10 power. Oh, they're asking answer in terms of mu naught only. Let's keep it as it is. So mu naught divided by 2 pi. D is 2.5 into I1 is 5. I2 is 2.5. 5 minus 2.5, 2.5, 2.5 will get cancelled. Then B net is equal to mu naught by 2 pi. Option C is the correct answer. Let's move on to the next one. Let's solve question number 47. A straight wire of diameter 0.5 mm carrying a current of 1 ampere is replaced by another wire of 1 mm diameter carrying same current. Underline this point. The strength of magnetic field far away is. What's the general formula for magnetic field due to a straight wire? It's mu naught I divided by 2R, right? So in this case, if you observe, R I is the distance. Sorry, no, it's not R. It is 2 pi A. Let's say A is a perpendicular distance from the conductor. Perpendicular distance from the wire. As current is same, I can say B is directly proportional to I here. As it is constant, then magnetic field is also constant. That means it is going to be same. There is no any kind of change here. So it's same. Option D is the correct answer. Next. If a long hollow copper pipe carries a current, then produced magnetic field will be. So for a hollow copper wire, magnetic field inside is going to be 0 and it is present only outside. Question number 48, option B is the correct. Outside of the pipe only. Inside there is no current, right? If you use, look at this. This is a hollow pipe. Is there any current inside? Current inside is 0. Current will flows on the walls of the pipe. So if you use amperes circuit law, it is going to be I inside. What is I inside? 0. So it is not suitable. So that's why magnetic field is present only outside, not inside. Let's solve next one. Two equal concentric currents are, two equal electric currents are flowing perpendicular to each other as shown in the figure. Okay. AB and CD are perpendicular to each other and symmetrically placed with respect to the currents. Where do we expect the resultant magnetic field to be 0? Okay. Super. Just use the direction of magnetic field, that is right hand thumb rule. Thumb indicates direction of current, curled fingers indicate direction of magnetic field. If I choose this point, I will give you one hint. So if I have a current carrying conductor like this, I said this in a previous session. So if this is the direction of current, right side magnetic field is into, left side out of. This is the trick that I am going to use here. So let me select a few points here. So this is the point. So this is the direction of current. So for this direction of current, as this point is leftward, magnetic field is going to be outward. So for this point is the right side of this let's say 1 and 2. Due to second conductor, magnetic field is into. So as both are of same current, so there is a possibility that I may get zero magnetic field at here. Okay, so there is a possibility B is equal to 0. And if you observe here, this is the point I am selecting, and this is how direction of current in conductor 1, and this is how direction of current in conductor 2. So as this point, right side of conductor 1, magnetic field is into, left side of conductor 2, magnetic field is outwards. Though there is a possibility here also magnetic field may be 0. Hope you are following. Now let me select point C. So point C is left side of conductor 1. So it's going to be magnetic field is out of the board. It is left side of conductor 2. Conductor 2 left side, in the sense I am talking with respect to current direction. So magnetic field is into the outside of the board. As magnetic field is in the same direction, is it possible for me to get B net 0? No, it's not equal to 0. So similarly, consider a point on D. So for conductor 2, it's right side. For conductor 1 is also its right side. So magnetic field is into, it is in the same direction. So B net is not equal to 0. Only possibility that we have is OB and OA. Which option? OB and OA is nothing but on AB wire. That's the correct answer. Got it? Next, question number 50. Magnetic field at a distance smaller from a long wire carrying current I is 0.4 Tesla. The magnetic field at a distance to R is. Question number 50. Magnetic field due to a straight wire formula is mu naught I divided by 2 pi R. This is the formula. As current is the same, this is magnetic field. As current is the same, I can write down B is inversely proportional to R. Then B2 by B1 is equal to R2 by R1. R2 is 2R divided by, it's not R2. So this is going to be R1 by R2. It is inversely relation, right? Let me replace it. It's going to be R1 by R2. So it is R1 is R, R2 is 2R, and B2 is equal to B1 by 2. It reduces. What is B1? B1 is equal to 0.4. 0.4 divided by 2 is 0.2 Tesla. Answer A is correct. So magnetic field is inversely proportional to perpendicular distance from the conductor. As distance from the conductor increases, magnetic field strength goes on decreases. Next, 51. Magnetic induction at a point P, which is at a distance 4 cm from a long current carrying wire, is 10 power minus 3 Tesla. The field induction at a distance 12 cm from the current carrying wire will be. Okay, it's a similar question. B is inversely proportional to R, right? So then B2 by B1 is equal to R1 by R2. R1 is 4 centimeter. R2 is 12 centimeter. So which is going to be 1 by 3. Then B2 is equal to 1 by 3 times of B1, where B1 is 10 power minus 3 Tesla, which can be replaced as 10 by 3 into 10 power minus 4, which is 3.33 into 10 power minus 4 Tesla. Option A is the correct answer. Let's move on to the another topic. Topic is the solenoid and toroid. For both of them, we have same formula, that is mu naught n I. Based on the type of the element, we are going to change the value of small and that. Okay, let's move on to it. 52. A long solenoid of 50 centimeter length having 100 turns carries a current of 2.5 ampere. The magnetic field at the center of the solenoid is. Formula for magnetic field due to a solenoid is B is equal to mu naught N I. They are asking at the center, right? It depends upon different positions. Okay. So we know the formula for mu naught 4 pi into 10 power minus 7, where n is n by l. Small n is equal to number of turns divided by l. L is the length of the solenoid. Capital N, number of turns are 100 divided by length is 50 centimeter. 50 into 10 power minus 2. Current is 2.5 ampere. So we can convert this. 1 0 will get cancelled. Remaining goes to numerator. It's going to be 10 power plus 1. So 1000. So 2.5 into 2.2. 2 will get cancelled. 2 pi into 10 power minus 4 will be there. 2 pi is nothing but 6.28 into 10 power minus 4. Tesla. Option A is the correct answer. Next question number 53. Two toroids 1 and 2 have total number of turns 200 and 100 respectively with average radii 40 cm and 20 cm respectively. If they carry same current, the ratio of magnetic field along the two loops. Okay, so magnetic field due to toroid is also mu naught n I, but only thing is this small n changes as 2 pi r. Here magnetic field due to a toroid is directly proportional to number of turns and inversely proportional to average radius. So you can write down B1 by B2 is equal to N1 by N2 into R2 by R1. Let me substitute. So toroid 1 and 2 have, first one is of 200 turns, second one is of 100 turns, that is 200 divided by 100 turns into radius. First one is of radius 40 centimeter, next 20 centimeter. So 20 centimeter divided by 40 centimeter. I think answer is the same. Yes, it is. Here is 20 twos are 100 twos are. So this 2 will get cancelled. B1 is equal to B2. Option A is the correct answer. Next, question number 54. A long solenoid carrying a current produces a magnetic field B along its axis. If the current is doubled and the number of turns per centimeter halved, the new magnetic field. Number of turns per centimeter is a small n. So B is equal to mu naught n I. B1 by, let's find out B2. B2 by B1 is equal to N2 by N1 into I2 by I1, where N2 is halved, right? That is N1 by 2, N1 into current is doubled. It means 2 times of I1 divided by I1. I1 will get cancelled out, and N1 also will get cancelled out. 1 by 2 into 2 will be there. This is also get cancelled. B2 is equal to B1 itself. So magnetic field remains the same. That is B answer. Okay. So these are the 3 questions based on solenoid and toroid. Let's move on to the next topic, that is force between two parallel currents ampere. So first of all, let me give you a formula for force between two current carrying conductors, let's say I1 and I2, separated by some distance d. Formula for force per unit length is mu naught into I1 I2 divided by 2 pi d. This is the formula for force per unit length. And one more point I would like to mention, if currents are in the same direction, force is attractive force. If currents are in the opposite direction, distance of separation d, then it's going to be repulsive. Remember this. Let's solve numericals based on this topic. An arrangement of three parallel straight wires placed perpendicular to plane of paper carrying same currents I along the same direction. Remember this point, same current and same direction as shown in the figure. The magnitude of force per unit length on the middle wire B is given by, as I told you earlier, if currents are in the same direction, then it is going to be attractive. If opposite direction, repulsive. Okay, then let me answer it. So currents are same. This is I, and I. So force acting on B due to A is going to be attractive force. So it's going to be downward. Force on B due to A per unit length. Meaning of unit length is length is of 1 meter. So I'm not substituting that 1 meter here. No need to worry about that. Next, force acting on B due to C is towards right. Force on B due to C. Attractive force, right? So these are the two forces which are perpendicular with each other. How to find out net magnetic field? And this is how the direction of net magnetic field B net here. Okay, so sorry, not B net, F net, right? It's F net. We need only magnitude. So F1 magnitude is equal to mu naught into I1 I2 is nothing but I square divided by 2 pi d. F2 is equal to mu naught I square divided by 2 pi d. As both of them are perpendicular with each other, F net is equal to root of F1 square plus F2 square. As these two are equal, let's say this is F and this is also F. Final answer is going to be F root 2. Then root 2 times of F is mu naught I square divided by 2 pi t. So you can convert this to as root 2 into root 2 again. Root 2 will get cancelled. So final answer mu naught I square divided by root 2 pi d. This is F net. So which option matches? Option C is the correct answer. Understood? Okay, next. Question number 56. A square loop ABCD carrying current I is placed near and coplanar with a long straight conductor XY carrying a current I. The net force on the loop will be. Okay. This is how the diagram is. First of all, to find out force acting on a current carrying conductor, we should know magnetic field, right? That magnetic field is produced by this current carrying a straight wire. So the total line represents here, it is of infinite length. So as I am moving away from this conductor, magnetic field strength goes on decreases. Let me name these conductors. Let's say this is 1, 2, 3, 4. Magnetic field on second and fourth conductor is the same. And one more thing, what's the direction of magnetic field here? Magnetic field is inward. This is how it is going to be. Observe carefully. Magnetic field due to a long straight wire. Right side of the current direction, magnetic field is always inward. And if you observe one more point, magnetic field on the first conductor is greater than magnetic field on the second conductor because conductor 1 is near to the straight wire, conductor 3 is away from it, but 2 and 4 are of a same distance. That's why magnetic field is same. So let me write down the direction of force acting on the each conductor. Use right hand palm rule. 4 fingers indicate direction of magnetic field, thumb indicates direction of current. Then force acting on first conductor is towards left. Let's say this is F1. Force acting on second conductor is upward, F2. On fourth conductor is downward, F4. force acting on third conductor is towards right. This is F3. As I said, B2 is equal to B4. B2 is equal to B4. Then F2 is also equal to F4, right? So these two will get cancelled out. No need to bother about them. Only thing we have to find out is F1 and F2. As B1 is greater than B3, F1 greater than F3. So we have to find out F net. We have to subtract F3 from F1. Sorry. Yes, correct. So F1 is force acting on a current carrying conductor formula B1 into I into L, where L is the length of that conductor, which is capital L, that is side of this length I have to consider. Okay, next minus B2 into I into L. As I into L is common, it will comes outside. What is B1 formula? Mu naught I divided by, what is the distance? It's due to infinite y, right? So it's going to be 2 pi r is L by 2, minus B2 is mu naught I divided by 2 pi L plus L by 2, 3L by 2. Mu naught I is also comes outside. Mu naught I small I into L divided by 2 pi also comes outside. 2 pi. Mu naught I by 2 pi came out. Now I am left with, this is 2 by L minus 2 by 3. This L will get cancelled out. So mu naught I divided by 2 pi into 6 minus 2, 4 by 3. So 2 cancel. So final answer is 2 times of mu naught I capital I divided by 3 pi. Which option? Option C is the correct answer for question number 56. Got it? Hope you understand the steps. Question number 57 is similar to question number 56. How? Look at this circuit. A square loop is placed just beside this current carrying conductor. So what kind of force it is going to experience? As I said earlier, force F1 towards left, F2, F3 right, F2 upward, and F4 downward. These two will get cancelled out. As I said earlier, F1 is greater than F3. Why? Because B1 is greater than B3, because B is inversely proportional to distance. This is the reason. So which force is greater? F1 is greater or F3 is greater? F1 is greater. That's why. So this complete loop experiences attractive force or repulsive forces? Experiences attractive force. Because F1 is greater than F3. Because B1 is greater than B3. Because B is inversely proportional to R. So for 57, which option is correct? Option A, I guess. Option 56 and 57 both are similar. Next, two long parallel wires are at a distance of 1 meter. Question number 58 is based on force between two parallel current carrying conductors. Okay, so observe over there. Let's say this is I1 and this is I2 and distance of separation is D. As I told you earlier, what's the formula for force? Force per unit length. Force per unit length in the sense. So F by 1 meter. I'm not considering that. Let's substitute it directly. Mu naught I1 I2 divided by 2 pi D. So F is equal to carry 1 ampere of current. That's what they are getting. So it's carrying 1 ampere of current. So 4 pi into 10 power minus 7 into 1 into 1 divided by 2 into pi into 1 meter distance. So pi will get cancelled, it is 2. So final answer F is equal to 2 into 10 power minus 7 newtons. 2 into 10 power minus 7 Newton per meter. Next 59. Two parallel wires in free space are 10 centimeter apart, each carries a current of 10 ampere in same direction. So this is how it is. Two parallel wires, each carrying 10 ampere of current in a same direction. If current is in same direction, what kind of force they'll experience? Attractive or repulsive? Attractive force. What's the distance of separation? 10 centimeter, nothing but 0.1 meter. Force experienced by one wire on the other per meter length. Okay, so that is F per meter length by 1 meter. So it's going to be mu naught I1 I2 divided by 2 pi d. 4 pi into 10 power minus 7 into I1 is 10, I2 is also 10 divided by 2 pi into distance of separation is 0.1, 10 power minus 1. So 2 pi 2. So 2 into 10 power minus 7. If it goes to numerator, it will be 10 power 3. 2 into 10 power minus 4 newtons. Attractive or repulsive? It's attractive because currents are in same direction. Which option matches? 2 into 10 power minus 4 attractive. Option C is the correct answer. Understood?